All right, so we have invented an expression for our flux integral. Notice that this is 2D only because of the trick that we used to come up with our unit normal vector n. The problem in 3D is that if you have a curve in 3D, there isn't just one perpendicular direction. There's actually a whole plane worth of perpendicular directions, and then it's not clear what flux should mean. So we'll come back to that problem later when we are dealing with vector calculus in 3 dimensions in a more systematic way. At any rate, this flux integral is 2D only, which you can see clearly here because we have a 2-dimensional vector. All right, so our idea for what flux should mean is f dot n ds, but when we parameterize it to actually calculate it, it will be f dot y prime comma x prime dt. Okay, so let's calculate one of these. Let's start out by finding the flux of this vector field across the line cosine t comma 2 sine t for t from 0 to 2 pi. It turns out this parametric curve, right, it's almost a circle except the radii in the x and y directions are different, and that means that it's actually an ellipse. So this has a radius of 1 horizontally but 2 vertically, so it's going to be like this. Excuse my terrible ellipse. It's going to be something like that, and we're going around this in the counterclockwise direction. So just based on this, we can estimate whether we expect the total flux to be positive or negative. We're going around this in the counterclockwise direction, and if you look at the vector field around this curve, the vector field is mostly pointing outwards. In fact, it's always pointing outwards. Not always perpendicular to the curve, but it is always pointing outwards, and so the total flux should definitely be positive. So when we finish our calculation, we ought to get a positive number. So let's actually do the calculation. So we're going to integrate f dot n ds, which is going to be the integral from 0 to 2 pi of f of r of t. I'll write it out in detail once, dotted with y prime comma x prime dt. So integral from 0 to 2 pi of, okay, so 3x. Remember, we need to plug our parametric curve in there, so x is really cosine t. So cosine t, comma, 1 plus 2y, and y is really 2 sine t. Okay, dotted with y prime comma x prime. So y prime is 2 cosine t, and x prime is minus sine t. Okay, dt. Now we can compute our dot product. So integral from 0 to 2 pi of 2 cosine squared t plus, I guess, minus because of this minus sign right here. So minus sine t minus 4 sine squared t dt. Okay. This is a little unfortunate because the 2 here doesn't match the 4 there, so we don't get nice simplification using the Pythagorean identity for sine and cosine, but we do have double angle identities. So cosine squared is 1/2 1 plus cosine 2t, okay, minus sine t minus 4 times, and then sine squared is 1/2 1 minus cosine 2t dt. So let's see if we can simplify all this. We have these cancel, so we have a 1. These combine to give us a 2. So there's 1 minus 2, so that's going to be a minus 1 for our constant. Looking at the cosine 2t's, here we have a plus cosine 2t and here we have a plus another 2, so that's plus 3 cosine 2t, and then we have minus sine t. And we're going from 0 to 2 pi. Okay, now finally we're in a position to do an antiderivative, so we're going to get minus t plus 3 halves sine 2t plus cosine t, and we're going to go from 0 to 2 pi. Right. Well, when we're going from 0 to 2 pi, when we plug things into our trig functions and simplify, things are going to cancel. So really we just need to concentrate on the minus t part, and that's going to give us minus 2 pi. Why did we get something negative? We said we were supposed to get something positive. What did I mess up? What I messed up is that I didn't put a minus sign on the x. So probably you saw that a long time ago and you've been yelling at me for 5 minutes. So this should be negative. That means this should be positive. That means this should be positive, and this should be positive. This should be positive, and this should be positive. So that means, let's see, we have a 1 plus 2. So this is going to be 3, not minus 1. And here we have a cosine and a minus 2. So this is minus 1 cosine 2t, and this is positive. Okay, so that's going to make this positive 3t plus some trig stuff. So these constants will change, but still when we plug in the bounds, these parts will all add up to 0. So we're going to get 6 pi. There, I fixed it, I think, hopefully. Okay, notice that, right, if you have a picture, you can catch silly mistakes like this if you think about what the answer should look like just based on the picture, right? The only reason I caught this mistake was because at the beginning I thought, okay, this ought to come out positive. When I did the calculation, I got something negative, and that clued me into the fact that I made a mistake, so then I could go find it, right? You should always be a little suspicious of your own calculations because it's so easy to make a mistake. So when you have a chance to know ahead of time something about what the result should be, take that opportunity. All right, so there's one example. Let's look at a second example. Let's find the flux of this vector field xy comma x squared minus y squared across the line segment from 0 minus 1 to 1 comma 0. So that's going to be, let's see, this line segment from 0 minus 1 up to 1, 0. And it's kind of hard to tell what is happening because the vectors in this area are so close. But in the first part of this curve, it looks like they're going this way, maybe. And in the second part of this curve, it looks like they're going that way. So it's actually hard to tell what the total flux should be because this first part should have positive flux and this second part should have negative flux. So here's a situation where actually we don't have a clear idea of what the result should be. So we're going to have to trust our calculation, so I'll try to be careful this time. We need to parameterize this. Line segment. So I think it's going to be something like, how about t comma minus 1 plus t. Okay, so this is obviously a line segment. The only question, and t is going to go from 0 to 1. The only question is, does it start and end in the right place? If it starts and ends in the right place and it's a line segment, then it must be the correct parameterization. So if you plug in 0, you get 0 minus 1. And if you plug in 1, you get 1 comma 0. So yes, this is a good parameterization for this line segment. And notice that it is going the right way. It's starting at the correct point and ending at the correct point. If we got those backwards, that would be bad. Okay, so now that we have a parameterization, we can calculate the integral. So integral from 0 to 1 of f And f is x times y, so t times minus 1 plus t, comma, x squared, which is going to be t squared, minus y squared, which is minus 1 plus t squared. And then we need to dot that with y prime comma minus x prime. Y prime is 1 and x prime is 1, and so minus x prime is minus 1 dt. Okay, so let's simplify. So this is going to be minus t plus t squared, comma, when we multiply all this stuff out, the t squareds cancel, so we get minus 2t, no, plus 2t minus 1 for our y coordinate. Okay, dotted with 1 comma minus 1 dt. All right, now we can do our dot product, integral from 0 to 1 of minus t plus t squared, so first coordinate times 1, and then plus 2t minus 1 times negative 1 dt. Now finally this is a scalar, so we can simplify everything. So we have a t squared, we have a minus t, a plus 2, sorry, minus t, a minus another 2t right there, so minus 3t, and we have a plus 1 right there, dt. Okay, so did I get that right? T plus t squared minus t minus another 2t and plus 1. Yes, okay. And now we can integrate, so this is the part where you tune out and watch me do a calculation that we all know how to do, but nobody actually wants to do because it's grunt work at this point. Okay, and then plug in. When we plug in 0, we're going to get 0, so let's plug in 1. We get a third minus 3 halves plus 1, whatever that turns out to be, right? A third minus a half is going to be minus having a terrible brain fart. So this is going to be a third minus a half, which is going to be 2/6 minus 3/6, so minus a 1/6. Okay, there we go. I did it. I got it eventually. So it turns out that the total flux across this line, since it's negative, the total flux is actually slightly to the left, which is not at all obvious just looking at the picture.